Welcome and good evening, everyone. My name is Adnan, one of the volunteers of the PyData Jeddah chapter. I'm here with my team members, Yasmin and Hassan, Shada and Abdulillah. Today's meetup is titled Transformers from the Ground Up by Dr. Sebastian Raschka. Dr. Sebastian is an assistant professor of statistics at the University of Wisconsin-Madison, focusing on deep learning and machine learning research. He's also a contributor to open source software and the author of the best-selling book, Python Machine Learning. Thank you, Dr. Sebastian, for joining us. And also we want to thank our sponsors, NumFOCUS and Muzun. If you want to visit our PyData Jeddah website or follow the Twitter account to be updated about our new upcoming meetups. And we also post a lot of cool things on there. And I guess that's all from me. I'll stop sharing so Dr. Sebastian can start. Thank you.
Yes, thank you so much for the kind introduction. I really appreciate it. It's my pleasure to be here. Thanks for the invitation. So I will start then by sharing my screen. And if there's some issue, please let me know. I can then try to fix that. So it should be visible now. Can you see everything?
Yes, it's clear. Yeah.
Oh, perfect. Great. Okay. Yeah, then I will get started. So today the talk is about transformers, the natural language processing models in deep learning. And I'm trying to cover transformers from the ground up, like explaining a little bit how they work. And then also, I hope we have time for that at the end, showing you an implementation in PyTorch. Why this topic? So I personally got very interested in this topic recently, and I was also working on the new edition for my Python machine learning book and was just putting together the chapter and had this very long lecture at my end of the semester last semester when I was teaching the deep learning class. And this is essentially more like a condensed version of that, highlighting the main concepts by skipping over the mathematical details, which I think would take too much time to digest. It would be more like a week-long effort to dig through all the details, but I hope this will give you like a good idea of how transformers work and also helping you like navigating the jungle of all the terminology a little bit, because there are so many different models out there like BERT, GPT version 1, GPT version 2, and you might wonder how they are different and what you can do with transformers. So just to start, a few examples where transformers are used nowadays. So one popular example would be language translation. That is also how the original transformer architecture was developed. So language translation was the main motivation behind developing the original architecture. And nowadays transformers are pretty much everywhere when it comes to natural language processing. And even beyond that, there are many real-world applications of transformers. For example, recently I also saw this article. So I'm also working in computational biology problems. Recently there was this article on using transformers to kind of elucidate or decipher properties in proteins, like organizing proteins by structure properties, but also by function. And they trained, for instance, transformers on a large scale database of amino acid sequences, like protein sequences, and they found all kinds of interesting insights from that. And you probably have seen recently the GitHub Copilot project. I think this was in collaboration with OpenAI and I think also Microsoft, where they trained a transformer to generate code. So here what is interesting is that you can essentially enter a query, a code comment, and this AI system, the model, will generate the corresponding code here at the bottom. So if you go to this website, they have like a nice animation of how that works, and they have a Microsoft Visual Studio Code plugin where you can download this and actually use that in action, which is really impressive. So I think right now they have JavaScript support and Python support. So that would be another interesting application of transformers. So transformers mainly are about generating things like generating translations or generating code, generating text, for instance, also in chatbots. But you can also use them for classification, like classifying, let's say, whether a movie review is positive or negative. And this will be a code example we will be covering at the end of this lecture or talk. So the topics I have in mind for today are those. So first, I wanted to, from the historic perspective, just briefly explain how attention came to be. So there was essentially this attention mechanism that was first added to recurrent neural networks. And then there was this self-attention mechanism, which is I would say, a more sophisticated version of that. There's this so-called scaled dot product attention. Oops, I almost ripped off my microphone here. So, and then we will talk about the original transformer architecture, which is the first architecture that was just using attention. So in step 1 here, this is a recurrent neural network augmented with attention, and the transformer is then an architecture that's just using attention without any recurrent neural network layers. And then I will briefly dive into some of these large-scale language models, for example, GPT and BERT, which are pretty popular these days. And then after that, we will we will fine-tune a pre-trained BERT model in PyTorch. So one thing about these large-scale language models is that they are really large scale and it would take forever to train them. So in practice, usually they are trained on large data sets, thousands or millions of websites and books and so forth. And so usually people download a pre-trained version and then fine-tune it to a target task. So we'll also take a look at how that looks like. And then I have a few closing thoughts or words on transformers. And with that, I think we have plenty of things to talk about in the next, I would say, 40 minutes. So to get started with the attention mechanism that was, so first, a small disclaimer here. So like I mentioned in the beginning, so this will be more like a conceptual overview. So if there are some, let's say, notational details in these figures, don't worry about them too much. To be honest, I think it's most important to kind of understand the big picture and all the mathematical details. That is something that are almost like implementation details. Some of them are almost arbitrary. So I wouldn't worry about it too much. But I hope this talk kind of piques your interest in terms of transformers. So if you're interested in that, you can dive in deeper into the topic afterwards with having this big picture overview in mind. So starting with the first topic, augmenting the recurrent neural networks with attention. So first, what is the motivation behind using attention? Why don't we just use recurrent neural networks? So if you think of a task, sequence-to-sequence task, which is a task where you have an input sequence and you want to generate an output sequence. One common example of that would be a language translation, where you have an input sequence, let's say this one here in blue, in one language, let's say German, and you want to translate this into English. So here on the output, then you have an output sequence. And what happens is if you use or if you design an architecture for that, you usually use this encoder-decoder setup in RNNs. So that means that the RNN first ingests the whole input sequence. So you have input element 1, 2, and 3. So these are, for instance, individual words. And they are then processed into these hidden states. And once you have processed the whole input in this encoder, so this would be essentially the encoder part, you have all the information in one hidden state here. And then you have the decoder part, which generates the output. So one might wonder, why don't you translate this one by one? Because here one problem would be that this hidden state has to remember all the input in one hidden state. And this might be a little bit overwhelming, right? So if you have one hidden state that has to capture the whole input, there might be some information loss. And this is essentially one of the challenges of these RNNs. They work kind of well if you have short sentences, but the longer your sentence becomes, the more challenging it is for the network to generate a good output, because it kind of forgets what happened, let's say, here in the very beginning, if you have a very, very long input sequence. So then also, why don't we just translate a sentence word by word? So here's just one example. Because I only speak 2 languages, German and a little bit of English, I have a German to English translation example here. So it's just an attempt translating this German sentence here at the top into an English sentence. And you can see what happens if you translate this word by word. So it doesn't really work. So you have a sentence. I'm an English as a second language speaker, so I'm usually also not that good at that, but I can tell that this one is definitely wrong. So you can see here the sentence is, can you help me? Can you help this sentence to translate? It doesn't really make sense if you just, let's say, take a dictionary and translate word by word. So to have a correct, I hope this is correct, if you have a correct English translation, the sentence would be, can you help me to translate the sentence? And you can see there is some longer range dependencies. There are some words here, for instance, those that you can just translate word by word, but then you have, let's say, these two here, where they are kind of flipped. So in order to translate this word, the help, you have to look into the future, basically. So you have to find an element that is further away in the input sequence. Or for example, if you have this word here, it goes here, you can see there's a more longer range dependency. And the longer your sentences are, the longer these dependencies become. So in that way, we can't really have this word by word translation attempt, because it would not result in any meaningful or grammatically wrong translation. So going back, this is why we first read the whole input, because we need to have knowledge about the whole input before we can attempt the translation. But then again, the challenge is, okay, we may forget earlier hidden states. So one idea to deal with this problem, that we can capture these long-range dependencies, is this attention mechanism. So this was first proposed in the context of RNNs in 2014. So I will share my slides, so if you are interested, you can look up these papers and read a little bit more details about that. So there was this attention mechanism that the researchers used to augment the RNN to better process the input. So here's just like a sketch in the lower left corner. For instance, if we are thinking of the second step here, the hidden state might have access, or at this step in general, you might have access to the whole sequence. I used just different line widths to denote that one input sequence might be more important than another. And this is where the attention comes in. So one step will have access to the whole input, but with a weighting term that says, okay, maybe at this position, this term is more important than, let's say, this term, and so forth. So not every word is equally important. So there's also some sort of weighting. And the architecture looks approximately like that. So this is a sketch I made after the paper. So it's just a little bit different notation, but essentially what we have is we have an input sequence. So this is just individual words, 1 to T words. And then they have two RNNs kind of connected here. So there's one RNN, it's a bidirectional RNN. Bidirectional RNN is just a fancy word for an RNN that processes the sequence from left to right and from right to left. It's just so that it captures information from both ends. It's just increasing the amount of information you have, essentially. So the forward direction would be the regular RNN direction. And then you essentially just flip the sequence and process it backwards. So this would be denoted here. So you can denote it from right to left, but you can also think of it as just reversing the sentence and processing it in the regular way. And then you connect these hidden states, and then you calculate the so-called attention weights. I will skip over the details of how these attention weights are computed here, but I will show you how they are computed in the transformer. It's a little bit different, but not too different. So, but the main part here is really that using these attention weights, we obtain the so-called context vector at each step. So the context vector here is essentially a weighted version of all the inputs. So you can consider all the hidden states here, and it's essentially a weighted sum. You have this attention weight, you multiply it by this state, and then you just sum them up. And the larger the attention weight, the more the hidden state will contribute to this context vector. So this context vector is essentially then kind of capturing all the input information in a certain processed way. And this goes into each decoder part. So if I go back a few slides, we had this decoder part here where we were generating some output. And this is what we are having here at the top, the O's. They should just denote, let's say, the translated sentence. And in each output step, what we have is we have the hidden state that goes into, let's say, that position, the previous word, because it's also important. I mean, if you generate a sentence, you kind of look at the previous word you have just written, right? So what you currently translate, the current word, is also depending on the previous word you have written. Otherwise, the sentence might not make sense. So you provide the previous word, you provide the hidden state, and you provide this context vector. And with that, you can capture all the input when you attempt the translation of the next word. So this is essentially an enhanced version of a recurrent neural network for translation, where this part here is essentially new. It's this attention part. Yeah, and from this attention part, people then develop this self-attention mechanism. So the self-attention mechanism is one major building block of this original transformer architecture that we will cover. And it's kind of inspired by this RNN that I just showed you. So here's a very simple version of self-attention. It's not the version that is actually used in the transformer that comes in a future slide. This is a simplified version just to understand the main concept. So what you can see here is, so to cover it step by step, there are 3 steps. And the first one is computing these dot products. So imagine we are currently processing a given word, xi, and we compute the similarity of this word. This is how we get a certain score for computing the attention weights. We compute the similarity of this to all the other words, including itself. And so what we have here is a sequence of words 1 to t. And why are there 4 blocks there? So the 4 blocks, they just denote that this is a vector. So it's, for example, a word embedding. So usually when we do natural language processing, we don't really feed it in the string of the word. So we usually have a method that converts the string, let's say, to a vector of real numbers. And this should just denote a word embedding here. And then there's this this dot product between 2 word embeddings, 2 vectors that we multiply. And let's say this gives us the attention weight. So it's just a simplified version. Usually we would use something like a softmax function, which is a function that would normalize them so that they sum up to 1. And from that, we then again compute the weighted sum of these. So we have these attention weights, and then we have our vectors, so vector 1 to t, and we just weight them by the corresponding attention weights. I should say also we have a specific attention weight for each query. So if let's say xi here is my query, these attention weights will be different compared to if x2 is my query, because it depends on the dot products, right? So these would change. Each word has different embeddings. So every query has its unique attention weights, and from that we derive this context vector, which is kind of similar to what I showed you in the RNN example. So this is a simple form of self-attention where we just introduce some weighting of all the inputs when we compute some output for a current word. So one problem with that, though, is, so the main takeaway here is that we compute these attention weights, but one problem is that we don't have any mechanism for training a neural network now, right? Because there is no weight parameter involved. So how do we improve this? How do we use, let's say, backpropagation or gradient descent with that to learn the optimal attention weights, for example? So for that, we in practice actually use a different type of attention. It's called scaled dot product attention. It's one form of self-attention with learnable weights. So this involves weight parameters. And there are then 3 matrices. And with these matrices, you compute also again like a vector, a query, a key, and a value using the input query. But here now these matrices are weight parameters that you can update during backpropagation or gradient descent to optimize the model. So here, what's going on here is we have a current input query that we are currently processing. Let's say the second word here again. And from the second word, we apply these 3 matrices to compute 3 values or 3 vectors. So a query, a key, and a value. And using those, so what we do then is we use the query first. So this query to compute these omega values. These are kind of like unscaled attention weights with each key. So the key is computed for each input word again. And we compute the dot product between query and key. But notice here we always use the query 2, which is our current word that we are processing. So we again obtain these unique values or unique attention weights for each query that we are currently processing. And then there's some normalization steps. So this is scaled dot product attention. It's a softmax with a scaling factor essentially. And then again, like before, we are summing them up to this context vector z. So this is essentially the same that I showed you here, except that it now involves these trainable matrices. And this is Yeah, this is the basic building block behind these transformer networks. So yeah, it's maybe a little bit fast, but to be honest, there is really not that much behind the self-attention. It looks maybe a little bit complicated, so maybe you need to look at this a little bit longer. It took me definitely some time to understand what's going on there. To be honest, a good way for me learning about that was really like reading the paper and then doing these or making these figures and drawing that to kind of make sense of it. But yeah, once you take a look at this, it's actually not as complicated as it looks like. I think the complicated part here is more like that these language models are so large, and if you look at the code itself, it's kind of like overwhelming because there's so many things going on there in the code, not in the building block here. So now to get to the original transformer architecture, which is built on this self-attention mechanism. So this is based on this paper, Attention is All You Need, that started all the trends in terms of developing transformers. It's a very influential paper that came out in 2017. It's not too long ago, 4 years ago. And since then, there have been hundreds, if not thousands, of different transformer architectures. But yeah, the main part is essentially that this is centered around this self-attention mechanism, and it does not use any RNN parts. So there's no recurrent neural network layer, nothing. It's just using the self-attention concepts and stacking them, and then also having some fully connected layers like in a multi-layer perceptron, just the very basic neural network layers. And here's a sketch of how the transformer architecture looks like. So yeah, like I mentioned, it looks very complicated at first glance. There are a lot of boxes and lots of things connected to each other, but essentially it's again not too bad. It's relatively straightforward. It's actually, again, our encoder and decoder, like in the RNN that I showed you earlier, where the job of the encoder is to ingest this input sequence, and the decoder job is to generate the output sequence. And yeah, what you do first is you have a word embedding, for example, to embed the words into real valued vectors. There's something like a positional encoding, because the problem is it's permutation invariant here, but we will skip over these details. It's just like a way of encoding the position of the word. So then we have this so-called multi-head attention. It's kind of like, I would say, an extension of the self-attention mechanism. I will have a slide on that to briefly explain what that is. Then there is a layer normalization, and yeah, like a multi-layer perceptron, a fully connected network. And then again, a layer normalization and so forth. So it's just repeating some of these units. And in between, we also have something like these arrows here connecting things. And these are skip connections. It's essentially just, this is what the add stands for. It's taking this value and adds it back here. It's similar to what a residual network does, if you have heard of a residual network. It's just like a means of preventing, let's say, bad gradients. So if you have something like a vanishing gradient problem here, then this one will be added to this one. It's kind of like skipping layers. If the layers are bad, then there's an opportunity to skip them via these connections. So to prevent bad layers from ruining the whole network. And then, yeah, this encoder, this captures essentially the input in this self-attention weighted way. It's like an encoding of the input. And this feeds into the decoder, which has itself also multi-head attention. There's a masked version, which I will also talk a bit about. Yeah, and this is essentially it. So it goes again through a fully connected network, and then there's a fully connected layer to produce the outputs. So the fully connected layer is then producing word probabilities with a softmax function, like how likely is this word at a given position. And then in practice, we usually use the highest probability if we, let's say, do a language translation, or if we generate text in general. If we want to have some randomness, we want our model to generate different texts, we could also just sample from this distribution. But yeah, in the original transformer architecture, what they had in mind was language translation. Yeah, to dive a little bit more into this multi-head attention, it sounds like it's a whole new concept, but it's essentially just our self-attention mechanism. So here, this is the scaled dot product attention that we talked about earlier with these different matrices. And multi-head attention is just repeating this multiple times. It's basically a stack of these things. It's kind of like similar when you if you have worked with convolutional networks and you have an input and you apply multiple kernels to produce multiple feature maps as the output, it's kind of like the same concept that each channel captures different type of information here. So in that way, this is a similar concept where you just repeat the self-attention multiple times and stack it up to each other. And this helps extracting different features that are useful. And one thing about that is what's also nice is that here, when we have this stacking, what the advantage is we can parallelize that, because there's no dependency between these individual scaled dot product attentions. So you can compute this in parallel. It helps us also to leverage multiple GPUs, for example. And for that, there are these so-called heads, attention heads, and each attention head has essentially one set of these matrices. So if we have H attention heads, we have H sets of these matrices. And then we just repeat the same thing multiple times. And also, I should say here, this is 6 times. So these blocks are also repeated 6 times. And I think this is what makes the architecture so big and complicated when you look at the code. If you look at a, let's say, from scratch implementation, it's just there are so many layers and there's just so much code that implements all of that. But the underlying concepts, if you draw them out, they are not themselves, they are not that complicated. It's just matrix multiplication, and then softmax and matrix multiplication. I will talk a bit about this mask maybe here. So the masked multi-head attention is masking out words that we haven't generated yet. So we have a target sequence that is our, let's say, desired output that we want to generate. Let's say if we want to translate something, but at a given time step, we don't want to have something that is in the future. So if we generate a sentence, let's say, let's say have a sentence help me translate this. So first we would have then, let's say, a German version of that, but let's say this is our target version. So in the first step, we would only have access to help, and then this one would be masked out. And then at the second step, we would have access to these 2 words, and these would be masked out. And the masked multi-head attention is essentially ensuring that future words that are not generated yet are masked out. I have actually a slide about that. And this masking out, this can also be considered as a unidirectional form of language modeling, because we are masking out everything that is in the future from the current position. So we are masking out from left to right. So it's kind of unidirectional. And we will also talk about a model that has a so-called bidirectional approach. So the BERT model has a bidirectional approach, and we will revisit this topic. It's kind of it sounds actually fancier than it is. So we will see in the future what this bidirectional means also. Okay, so this was already all the original transformer stuff I wanted to talk about. And these were all the original ideas, like from a historic perspective. So nowadays, people don't use this original transformer architecture anymore, but there are many, many other architectures that have been inspired by this architecture. So here in this section, I want to briefly highlight some of them. So one is this GPT model developed mainly by the OpenAI team. And this takes this unidirectional approach, which is kind of similar to the decoder of the original transformer. And this is used for tasks that involve generating texts. You can use it for classification too, but mainly the focus is on generating text. And then there is the BERT model, and of course there are other different types of versions of it. For example, Roberta and Alberta and so forth. But in general, the BERT model is a bidirectional approach, and this is more suited or better suited for classification tasks. For example, in the code example that I prepared, where we predict whether the movie review is positive or negative. So whether someone liked the movie or not. But one scheme that is common amongst most transformers is that there are 2 steps. One is a pre-training step on very large unlabeled data sets. And then there's a fine-tuning step where we take a pre-trained model and then we train it on our target data set. So here in step 1, this is usually a general data set that is not really related to our target task. It's, for instance, just a library of books or websites. but we don't have any labels. And yeah, this is just used to pre-train the model. They are very large models, so they need a lot of data to be kind of yeah, pre-trained. So, and for this training, there are these two steps that I mentioned, the pre-training and the fine-tuning, 1 and 2. And the fine-tuning can also be split into 2 different approaches. And both are very common. I think fine-tuning is a little bit more common, performs better, but it's also more expensive. So one is, yeah, this feature-based approach, and one is this fine-tuning based approach. So how do they differ? So assume you have step 1 where you pre-train your transformer. So this is sometimes called, in the original literature, it's called unsupervised pre-training, but the more modern term for that is self-supervised learning. So the same thing essentially, where you train a model on unlabeled data. And then, so the data is unlabeled, but it's still a supervised learning approach. This is why it's called self-supervised learning. So you generate essentially the labels yourself. So you take, let's say, a book, and then you train the model to predict, you remove some words, and then you train the model to predict missing words, or you predict the next word in the sentence. And the next word in the sentence would be your label, but it's not like a label for classification. It's just like a label that you can generate yourself from the text. You don't need to have a human labeling these texts. Yeah, so, and then let's assume we have now our pre-trained transformer here in this red block. So then once you have it pre-trained on a large data set, you never have to change it again in terms of, so you basically save that somewhere on your computer, and then you can use it for all your downstream projects. That is what I mean. And one way is to never really change it. You take it, and then you just extract the last layer. So you give it a new sentence, and then you extract the output layers, 1 or more output layers, you can concatenate them. And then you give these output layers to a classifier. For example, logistic regression, multi-layer perceptron, maybe a random forest, whatever you desire. And you only train this classifier. So you essentially treat this pre-trained transformer as a feature extractor. If you have used something like principal component analysis, this is also one method. Let's say it's a linear transformation of your input. It's one method to, let's say, extract some features from your original features. So it's in that way, the pre-trained transformer acts like a feature extractor, where you just use it to extract these last layers, and then you just train a classifier on top of that. Another approach is this fine-tuning approach. It's a little bit more expensive. This is for what I prepared this code example. So this fine-tuning approach is a little bit different in that you update the whole model. So you start with your pre-trained transformer. Let's say you saved it somewhere on your hard drive. You make a copy of that, and then you feed it the labeled training data set that you have, and you add a few layers for classification. Let's say if we have our movie review data set, we add one final node in the output layer, have a softmax activation, and then we just train the whole model with backpropagation. So we update all the model parameters. And because we have to load all the models, the whole model in memory, and do the backpropagation, it's a little bit more expensive than this step, where we only use the transformer for generating the features. So in that way, it depends. It's of course also slower. So it depends on what type of architecture you have access to use this approach. But in practice, it performs a little bit better. I think I forgot which paper it was, either GPT-1 or BERT. They also directly compared those approaches. I think it might be GPT-1, but I would have to double check. And they found, I think if you use the last 3 layers here, you can get approximately the same performance as with fine-tuning. So in that way, it's really, you can get the same performance, but it's really a trade-off also of how much computational resources you have. Yeah, so talking a little bit about the GPT models. So there are 3 GPT models now. So one was released in 2018, one in 2019, one in 2020. And yeah, if the sequence continues, we maybe have a new version by the end of this year. And yeah, one obvious thing you can see from these GPT models, which stands for Generative Pre-trained Transformer, is that yeah, they increased a lot in size. So they started with 110 million parameters, which was already really huge. Then the next one had 1.5, and now we have 175 billion. So who knows, maybe the next one is in the trillion range. So if you're interested, like I said, I will share my slides later, so you can also read more about that in the original manuscripts. But yeah, just to give you just brief summary of how these models work, I have a few slides on those. So GPT-1, that's the first model in this series. It's essentially very similar to the transformer we talked about. Especially, I mean, it's just taking the decoder part. And yeah, it's trained on a sentence in this next word prediction manner. So the pre-training is taking a large context or a large corpus of books or websites, I think. I think they used a mix of words from websites and books. And they have these sentences where they remove, through this masking, the future words, and the model's task is to predict the next word. And they just train the model in this manner. So they train it just for this prediction of the next word in the sentence. And after doing that, you can then fine tune it. So you add, so for having this task classifier, you can add additional layers after you pre-trained the model. And depending on what you're interested in, is you can do a classification, entailment, similarity, multiple choice questions, and so forth. And how that works is essentially they have this pre-trained transformer here, and they just connect the linear layers, and then it's like a regular classifier. And yeah, one thing here is, I won't go into too much detail, but it's how you format the input. If you have a classification, you have like a start token, a text, the sentences, and then some extraction token. And if you have something like similarity here, text similarity, they have both texts and then in flipped order, for example. So it just differs a little bit about how you set up the inputs. But yeah, the main thing is that you can just adopt this pre-trained network to do whatever you like in the fine-tuning. So this is really expensive. This is like a really expensive step. That's something you don't want to do yourself. You want to maybe download this GPT, and then you can, on your target data set, do the fine-tuning. Yeah, and then really what was really novel about GPT-2 and GPT-3 is that they actually removed this fine-tuning. Most language transformers, they use the fine-tuning step that I talked about. What GPT-2 and GPT-3 are doing, though, is they tried something new. They were so ambitious that they kind of removed this fine-tuning, and they only have a model now where you provide what you want to do as input. So for example, if you want to use their model, the GPT-2 model, to generate text, what you do is you give it an input that is formatted as follows, where you say to the model, translate to French, and then you insert your English text, and then you insert your French text, and it will automatically figure out what you want to do, basically. And you can ask it also different questions, like you give it a sentence and you can ask something like, is this object, so you can say, for example, this is a very nice sky, and is the sky blue? And it can generate like an output that says yes or no or something like that. So it's kind of very flexible in terms of what it can do by only having a certain formatted input without any fine tuning. And version 3, I think they kind of went back a little bit, because I think, so here, this is called, in this context, zero-shot learning, where they don't have any examples of the task. The example is in, or the description is in the task itself. They don't have any training examples in that sense. But I think this was maybe a little bit too ambitious. So they went back with GPT-3, made it a little bit bigger, and they switched also to few-shot learning in this context, where in the few-shot learning, they have at least a few examples of that task. So just to illustrate how that looks like. So here is this zero-shot, where you have, again, the prompt or task description, sorry, and then a prompt. And then it would insert here the French word for cheese. I honestly don't know any French, so I can't tell you what it is. Oops. But yeah, it would generate this output here. And for the one-shot, it's a little bit more, I would say, easier for the model, because it sees at least an example. It's not fine-tuned, it's just seeing the example as part of the input. So you have, again, the task description here at the top. Oops. And then you have one example of what you want to do. And then you have the prompt. Then few-shot learning. So if you have, let's say here, a three-shot case where you have one example, second example, the third example, it becomes easier for the model if you showed at least a few examples. See, there's just a note in the chat. I will maybe answer the questions after the talk. I'm, I think, almost over time, with a few slides left. yeah, so here, well, where was I? So yeah, here the limitation of the few-shot tasks though is that you have a limited size input. I honestly don't remember what the size is for GPT-3. I think they have some APIs that I have never used. But let's say for BERT models, there's a token input limitation of 512 tokens. It's like characters or word, not characters, but like words or punctuation. So in that way, you're kind of limited by what the model can process as input and how many examples you provide. So this is actually a fine, but I can imagine it's maybe a challenge if you have longer sentences here. So that wouldn't probably work with very long sentences, because then you fill up all the input with examples. And this, yeah, this is in contrast to the fine-tuning approach with which most other transformers use, where you have an example as part of your training set, and then you update it with backpropagation, like the gradient update, show it another example, and so forth. So this is more like the traditional way of doing it. And yeah, the GPT-3 model is very ambitious, and I think, I'm not sure if actually the paper is out yet, but yeah, this is one of the latest state-of-the-art models for generating texts. And another approach is the BERT model, which is a bidirectional encoder. So you can think of GPT more as the decoder, which generates some output, whereas BERT is more like the encoder of the transformer, which ingests like the input and then creates a representation that you can then use to train a classifier on it. So GPT is better for generating texts, BERT is better for classification. So how that works is they have a pre-training step, or they have actually two different types of pre-training tasks. One is this masked language model. So what they do is they mask 15% of the words. I like to call it marked, not masked yet, because what they do is they take these 15 words, or 15% of the words, if you have a sentence, and then they do different things to it. So here's an example. So let's say this is a sentence here, an input sentence. You would randomly pick 15% of the words. For example, you would pick, let's say, fox. And then based on these 15%, what you do is 80% of the time, you replace this token, the fox, with a mask. Then 10% of the time, you replace it with a random word, for example, coffee. And 10% of the time, you keep it unchanged. And so this is how you pre-train the model. You have all these sentences, and 15% of the words are changed in a certain way, and the model has to predict what the correct word is at a certain position. For example, it has to fill in the right word if there's a mask, or it has to detect whether this word is right or wrong. And then sometimes it's unchanged. So why would you have this unchanged? So this is kind of important for the model in order to perform well during inference. When you train the model and you want to use it in the real world, you usually don't have masked sentences, and the model here also then basically learns that sometimes it should not do anything. So in order to work well also in real text, which doesn't have masks, otherwise it would always expect, okay, there are some random words or masked words. So in this way, they found that this performs better if they have also 10% of the masked or marked words unchanged. And the second pre-training task that they do at the same time is next sentence prediction. So they have a sentence A and a sentence B separated by a token, and the model has to predict whether sentence B indeed follows sentence A. So if you have a text and you reverse the order of the sentences, the model learns the correct order, and this helps the model to work with inputs that are more than one sentence. So it's essentially a classification, a binary classification, is next or is not next, essentially. And yeah, this classification token is used as a placeholder for generating the output, because the number of inputs also matches the number of outputs. But in BERT, we are not interested in generating new text. We are essentially interested in classification. So how that works, here's just a brief overview of different types of tasks you can do with BERT. So one is sentence pair classification. One is just a single sentence classification, question answering, and single sentence tagging. So here tagging is, for example, if you think about something like language, a grammar software, you can label a sentence by what type of, like a verb or noun, what type of word or grammar each word corresponds to. But let's focus maybe only here on the, because we have, for the interest of time, on the single sentence classification task. So you provided an input sentence, you have some embedding here, and then you provide some output. So you have, during training, you have all these tokens, so it has to repredict what the input is, given that something is masked or not. If you have a prediction task, you don't, I mean, it still generates the sentence, but you don't do anything with it. What you care about is this class label here. So this is why you have this classification token. This goes then into the class label that you care about. And this is something we can leverage for arbitrary classification. So I prepared a code example for fine-tuning such a BERT model for this single sentence classification in PyTorch. And I should mention it says single sentence classification. And for the code example, I have this large movie review data set. I mean, back then it was large, but it's just 50,000 movie reviews. And I think 25,000 in the training and 25,000 in test set. And this is essentially movie reviews from the IMDb movie review database. And these are multiple sentences. So we can also use BERT for multiple sentences, even though, let's say, it says single sentence classification, by just concatenating these sentences. So in that way, the only difference is we don't use this separator token, because the separator token is really more for comparing two things, like this sentence pair classification. So this one can, for example, say whether these sentences are similar or not, like sentence similarity and things like that. Yeah, so I'm not sure how much time we have. I could maybe briefly, went way over. I can maybe briefly show you the code example. It's actually not too complicated. I have it on GitHub. I have some annotation. It's based on a library called Hugging Face. It's a very, very popular library for. Oh, you probably can't see it now. I have to reshare my screen. Okay. Let me see how many slides I have left. So we probably don't have to cover this. Let me share my browser screen so you can briefly see the code example. Here I opened it from GitHub. I have also my Jupyter Lab version, which is maybe better because I can zoom in here. Keyboard. So here is a notebook for downloading a pre-trained BERT model and fine-tuning it on the movie review classification. There's a lot of boilerplate code here, like importing the libraries, some settings for reproducibility, downloading the data set, and then processing it. So here is a pandas data frame of how the data set looks like. There's like a text, a movie review, and then it's whether it's positive or negative, like a binary classification. We have 50,000 combined, and here I'm just splitting them into training and validation and test sets. Then there's a tokenization step. So tokenization goes from taking the words and then converting them, taking the sentence and chopping it into words, and then also taking care of punctuation. So punctuation is also, I think, given token, but it really depends on what type of tokenizer you use. So there's also a selection of different tokenizers out there. They all behave a little bit differently. But I recommend, if you use, let's say, Hugging Face, I recommend finding a tokenizer that matches your model. I should say we are using here not BERT, but DistilBERT. I think I had a note about that at the top. Yeah, DistilBERT is essentially a smaller version of BERT, because if you only have, let's say, one GPU, like 1080 Ti or 2080 Ti, like a graphics card with only 11 GB memory, I couldn't at least load the whole BERT model into memory. Or I think I could just barely load it, but then not train it. So there is a version called DistilBERT, which is a little bit smaller. So in DistilBERT, what they did is they trained the BERT model, and then they removed some weights, but preserving its performance. It has 95% of the performance of BERT, but it's more lightweight. It has 40% fewer parameters. Okay, so we are using a tokenizer that is made for this DistilBERT model, and then encode the data set into tokens. And then I have my data loader here in PyTorch. So this is a custom data loader. Here, there's nothing really special about it if you would build a data loader for any type of image data set, for example, except that the way we process essentially the encodings. So there's like a special representation that is, I think it's kind of like a dictionary. It's its own Python, so yeah, a Python object or class, but it kind of behaves like a dictionary. You can index into that, and I will show you how that looks like. So yeah, here's an example. You can have a so this will create a dictionary, right? But I think itself, it's also some certain object that contains multiple things. Yeah, so here I'm just creating data loaders from the data set. So this is basically all just set up. And here's the main part where we are loading the Dilbert model. And they have multiple models on their website if you go to the Hugging Face Transformer website. And here this would be, for example, a Dilbert model for sentence or sequence classification. You can basically tell based on the class name what this is made for. And then I'm loading it, the pre-trained version. And they have also, again, I think they have different ones. Uncased here would mean it would ignore sentence case, whether it's upper or lower case. Yeah, and then I'm putting the model on my device, putting it into training mode, and then initializing an optimizer for backpropagation. This is just a warning. It's, I think, I don't exactly know what they want here. I think it's just some hints. It's nothing really we have to be concerned about. And here I implemented an accuracy function. So what I'm showing you is like a manual training loop, basically how you would implement this in, let's say, your own PyTorch code. And then at the end, I will also show you a trainer class. I mean, we are almost done. It's just the last little bit here. So what I have here in this accuracy function, how I write my accuracy function is usually that I load the data in batches, because I usually have large data sets and you can't just put the whole data set into the model as input, because you would have then very large matrix multiplication and then you run out of GPU memory. So what I usually do is like similar to training, I batch up my data set into chunks, into these batches. It's automatically done by the data loader here. And then I compute the predicted labels and collect them. So I'm just collecting the number of correct predictions. And once I have summed up all the correct predictions, I divide by the number of training examples. So I keep track of the number of examples and use that to divide the number of correct predictions, and that gives me the accuracy. So it's in that way not requiring to load all the data all at once. And yeah, there are some interesting things here going on. So we have the input IDs of the words. We have the attention mask. So the attention mask is it's a little bit weird here. Why do we need an attention mask? So it's essentially for padding. So if we have sentences of different lengths, it will use zeros to do a padding. So it's essentially denoting which character is a padding character and which is an actual word. And then we get our class labels, and we provide as the model input the input IDs, the words. So the model itself will then do the word embedding and then the attention mask. And then we obtain from the outputs. The outputs is a kind of, I think it's an object, but you can index into it, might be a dictionary. So you get the logits, which you can then use. You could use the softmax function to get probabilities, but it's not necessary because the largest logit is also the largest probability in softmax. So you get the class label with argmax. It's your class label. And then I was just checking whether the predicted label is matching the correct label, the actual label. Okay, this is just how I compute the accuracy. And here is my training loop. So I usually have a very simple training loop because when I do research, I like to tinker with things. So I like to have like a more manual approach. This works similarly. I obtain my input IDs from the data loader, have my attention mask, the labels, compute the outputs. Here, in addition to the logits, I also need the loss for optimization. So you have to provide also the class labels as the model input. So I get both the logits and the loss. And then like in regular PyTorch, I use backward on the loss and optimize. And this is just for logging purposes. So when I do that on my data set, it trained for like an hour and gets like a 91% accuracy. One interesting thing is about that, briefly, I tried an RNN on that, and I think I got like 88% accuracy. So using this pre-trained model, even though it's a small data set, the IMDb movie review data set, even though it's small, I can use a pre-trained transformer to fine-tune it on the small data set to get performance that is actually better than, let's say, logistic regression, which was like 85%, and an RNN, which was like 88%. And I didn't do any tuning here, by the way. I just used it one time because I was short on time. I didn't do any learning rate tuning, nothing. So it worked kind of like out of the box. And then there's also, if you really want to use transformers seriously, I recommend using the APIs that Hugging Face provides. So they have a trainer class where you specify options in the so-called trainer arguments. And then you have this trainer class where you provide this as input and it handles everything automatically. So I also have a run here. And actually it got even better performance. I think they have some certain default parameters for regularization and so forth. So it was, first of all, faster, and also the performance was better. I think they have better default options because my training loop was very minimal. So they have some additional options. And actually, for comparison, there's a setting, I only used one GPU. When I was disabling that, one of my computers where I ran this had 4 GPUs. It was running in 16 minutes. So in practice, you maybe also want to disable that and you get also way faster training. Okay, so just briefly.
Sorry, Sebastian, we have less than minutes to finish, please.
Yeah, let's, sorry, I was going way over time. So yeah, maybe let's go to the
we will take some questions, yes.
Okay.
You can start asking the questions, please.
So maybe last thing is, I will just go to my slides for the questions also. Oops. Sorry, that's not the right one. But I am ready for questions now. So I wanted to say I have also a way more detailed transformer lecture on YouTube from my deep learning class, and there will be a version of the Python machine learning book coming out for PyTorch, which also has a transformer chapter that will be later this year. So if you want to read more details about this, also this might be a useful resource. Okay, yeah. So I'm also I wanted to mention the figures here. They are from that chapter, so I want to give also credit to GPT and BERT, who helped me a lot with the figures and writing this chapter. Okay, so sorry. So I think we can take questions now.
No worries. Hassan, you can start, please.
Yeah, thank you so much, Dr. Sebastian, for this wonderful talk. Now it's your time, participants. If you have any questions and you'd like to ask it to Dr. Sebastian, feel free to write it in the chat, or even you can raise your hand and we'll unmute you so you can ask your question verbally. So let's start with our first question for today. It is from Sunny. She's asking, can GPT do classification?
I think so. Yeah, definitely the first version. I think the other versions can do classification too. On the Hugging Face website, they have, I think, also an implementation of GPT, a re-implementation where you can try this out. I had this. I remember I have demonstrated this actually in spring semester in the class. So they definitely have capabilities to do classification. In GPT 2 and 3, you have to provide it via the context. But in GPT version 1, they also provide classification as an example in the paper. I'm not sure if I had a figure on this here, but yeah, you can. But people just, because the way it's trained in this unidirectional way, usually people agree that BERT type of models would be better for classification, although you can use GPT-2 for classification.
Another question from Marito Barata. Is there any use cases right now where transformers-based vision models outperform previous models like those based on ResNet? And should I use transformers architecture-based models now to classify images and replace ResNet?
Yeah, that's a good question. So I have seen a lot of papers recently using transformer models for computer vision. There's the classic vision transformer, and there are also newer models. And I think they are, depends on which paper you read, they are state of the art compared to computer vision models. I think the EfficientNet version 3 paper that came out in April showed that they performed better than transformers, but this was in April, so things might be different now. But one downside of transformers in computer vision is that they require more data for pre-training. If you can get the pre-trained models, it might be for the fine-tuning part, it might be worthwhile. But otherwise, I think it's more like a research topic now that people are exploring. in practice, it's probably very expensive to train them. I think there's also this paper, I'm not sure if they compared directly. So EfficientNet version 3 was better than the vision transformer, and there's the HaloNet paper that came out in June. It's like a ResNet 50-like architecture with attention, but it's not a vision transformer, but it has like ResNet-like backbone with attention. And I think this one outperformed EfficientNet version 3 on ImageNet. I think they got like 85 point something performance. So in that way, I think, yeah, it's right now really where transformers are. I mean, they are state of the art, but I think it's still worthwhile using CNNs for classification for the time being, because they're also, yeah, cheaper to train. And then, of course, we also have architectures like MLP Mixer, which is neither of them. It's just multi-layer perceptrons. So yeah, it's an interesting time, interesting question. I would say, personally, I stick with CNNs because they are easier to train, but in the future, who knows? I think maybe computer vision transformers will take over completely.
Great. Ritubhat is also asking, is transformer architecture practical for real-world tasks outside of US academia and big tech companies? And what are the next steps? Oh, sorry. And what are the next steps to make transformer architecture-based models more accessible? Will transformers be able to adapt, or something more pragmatic will replace it?
Yeah, good question. I think that is one of the big frustrations, that these transformer models are so big that as private person or in academia, it's really hard to train them. I think some labs in academia have large resources. For example, this paper here, I think the preprint was, I saw the preprint, I think for this paper like in 2019. So even 2 years ago, they had the resources for training that, but it must have been really expensive. I think they had like 50 GPUs or even 50 GPU TPU pods. I think they collaborated with big tech companies. But yeah, how do you as a normal researcher use these? I think it's really infeasible to use these pre-train these models as a private person. I mean, you can probably manage, but you probably need a whole team of engineers to even set up all the infrastructure to make this work. And in that way, I find it more interesting to really fine-tune these models, like training or using a pre-trained model and then just focusing on fine-tuning. And like you've seen in this code example I showed you, it's like in under than 1 hour you can fine-tune these models. But yeah, there are also approaches where people have made transformers way more efficient. I haven't covered them here because of time constraints, but there's, for example, the Nystrom former, or top of my head, the sparse transformer, which I think, yeah, they have usually you have quadratic complexity, they have linear complexity, scaling in terms of the input sequence size. So people have made efforts to make transformers more efficient. Or if I had a slide even on that here. There are efforts, so this is unfortunately capped clipped at 2019 here. But yeah, you can see there's this trend that they become bigger and bigger and bigger. But there are also some efforts, for example, the DistilBERT that I showed you, and other methods that try to reduce the number of parameters and allow people to use transformers even though they may not have access to large computer infrastructure. But yeah, it's like a concern many people are concerned about. There was also this paper calculating the cost. If you have a 1.5 billion parameter model, it costs like 80,000 to 1.6 million just to train this model. So yeah, we'll see where things go. But yeah, this is definitely a concern that this is really unfeasible for many people.
Nice. We have another question from Jisia. Can GPT-2 be fine-tuned on small data sets, like few hundreds?
Yeah, I think so. Personally, I have only used GPT-2 via the Hugging Face website, where they had like a derivative of GPT-2. I forgot the name. I think it's called GPT Neo. So this GPT Neo is like an effort by the open source community to train a GPT-2 model, because I think maybe it has changed, but I don't think they OpenAI has shared the full model. I think they only provide access through an API. So in that way, if you only have access to an API, I don't know if you can fine tune it. But there's this GPT Neo project. I can spell it out. I would have to search the website. I don't know off the top of my head, but I think it's spelled like this, where they have re-engineered either GPT version 2 or 3. And I think this might be something that you could download and fine-tune. And I think Hugging Face also has maybe some models. I would have to double check. I haven't done this myself, but I think it should be possible. Although for GPT-2 and 3, it's kind of not necessary because you have like these contexts. So they say with the context, it's sufficient, but you could maybe fine tune it. I don't know for sure. It's a good question.
Great. Alti is wondering if you can use pre-trained BERT for specific domains, like, for example, medicine.
Yeah, definitely. So this is, yeah. So you can definitely adopt the architecture for specific domains. So in that way, if you have a small medical image data set like texts, you could technically fine tune this. But if you have a large data set, you can also maybe try to train it from scratch, like the researchers did here. So here, instead of training it on sentences, they used the BERT model. I think this group, there were two groups that did something similar. They used the BERT model and trained it on amino acid sequences, where they had millions of sequences from the protein structure database. They were like, I mean, you can think of an amino acid sequence as a sentence, but each character, there are 20 different amino acids. Each character would represent a word, essentially, because it's more like a character level type of thing. But they did that and it worked well. So I can imagine you can also train it on other types of sequences. And in the medical domain, depends on whether you have a sequence of a specific domain-specific encoding. Let's say maybe you have a certain device that outputs certain values that don't, let's say, have a meaning to a human, but that could be passed by a machine. I can also think of a transformer maybe being trained on that. Or if you have just texts like annotations of patient records, I think that could also be done. So yeah, you can definitely train this on other things other than general text.
Great. Alti is also asking, when we fine-tune the pre-trained BERT, will that update the vocab of, if the initial vocab will be the same after fine-tuning?
The vocabulary, I think, a good question. So when you fine-tune it, so you have the text embedding, I think it would update also the embedding step. This is something I can't say 100% sure, because when you use this code from Hugging Face, the code from Hugging Face includes the encoding, as far as I know, because you only provide the input IDs of the words, and then encoding is part of the model. And if you update this, I think you should also, or it should also update the embeddings. I'm like 90% sure, but not 100%, because yeah, I haven't really looked at the code line by line. Maybe they have a line that freezes the weights for the embeddings, so that I don't know for sure, but I suspect the embeddings are also updated. Oh, sorry, I think the question might have been about the vocabulary size. So I think the vocabulary size is fixed. So I don't think this can be updated, because the vocabulary size depends on the input ID on the tokenizer. So I think if you have I think the tokenizer would remove words from your input text that is not included in the pre-training. So if you have some arbitrary words that are not in the database where the model was pre-trained on, I think you don't have to worry about it if you use the right tokenizer, because it would replace it by an arbitrary token. But of course, also the model wouldn't then be able to perform well on if you have a lot of different tokens, because these are tokens the model has never seen before, and they are all, I think, converted to an arbitrary unknown token or something like that.
Okay, nice. Alti, do you want to say anything? You can unmute yourself and ask any questions.
Can you hear me?
Yes,
yeah,
we can.
Sure.
Thank you. Sorry for insisting on this question, but I just wanted to return a bit to this point, to the last one, to the vocabulary one. My idea is that of a fast AI library, in which they have the NLP part of it together with the image, and actually they. Jeremy Howard has made this fast AI library in a way that when you fine tune the pre-trained model to a specific domain, then all the words that are not tokens, that are not part of the original vocabulary of the pre-trained model, will be added to the new vocabulary, and then will be they will train by like starting from scratch, let's say, no? Like as you do with the pre-training, but with this. But I'm not sure that this is the case for BERT, to be honest, because I've been asking the guys in some other talks like this. And as far as I know, they don't do that. And that is the original question, like, how well does perform BERT, pre-trained, let's say pre-trained BERT, when we fine tune it, I don't know, in medicine, when most of the characters, I don't know, in whatever other domain-specific task, when most of the words or tokens, tokens might be quite different, and they will be just unknown, no? It's like technical question, sorry about that. Huh?
Yeah.
And partly you answered, thank you, but just like, it's not about the size of the vocabulary, but like exactly this thing. Thank you so much.
Yeah, so yeah, I think that's a good point. I think they are kind of related. So I think in the BERT model, they basically have a fixed vocabulary where all the words appear that appeared during pre-training plus an unknown token. And then if you have during fine-tuning the new words, it will just be mapped to this unknown token, so they don't expand this vocabulary, right? That's what I'm suspecting. And you mentioned that fast AI, they would add it to the vocabulary, and then I haven't really worked with the fast AI version of this, so that sounds like a good approach right now. If you then have some really, if you don't want to maybe pre-train it completely from scratch, but you have a very different data set with different tokens, so you kind of it's kind of more flexible in that way, I would say. Yeah, that makes sense. Yeah.
Thank you anyway. Very.
Thank you, Alti. Again, if you want to ask any questions, you can raise your hand and we will unmute you so you can ask questions to Dr. Sebastian. Back to chat, we have a question from Anna. How to handle the bottleneck caused by data loader reading each example from memory?
Yeah, the bottleneck. So in terms of speed, yeah, you could increase. So what I do sometimes, if it's too slow, if I have a very large data set, what I would do is I would increase I would make a new data loader for the training set. If I want to compute the training set accuracy, I would have a second one, which has just a larger batch size than the one I used during training. And for the test set, I would just set the batch size really large as it goes until it crashes, because at some point it would just crash. But in a case like this, I would say it's not really a bottleneck. It's I mean, it takes maybe under a minute or maybe a few seconds to process the whole data set in each epoch. And we are only computing in the accuracy function like the performance in each epoch, so it's not like too often. I think this is reasonable, but maybe the question is also about like how we deal with that bottleneck during training. That's a good question. I actually, yeah, that's one limitation. So I could only go up to batch size 16 here in this example, because otherwise I would run out of memory. So one way to deal with that would be choosing a different type of transformer, for example. So there are more efficient transformers that have fewer parameters and smaller maybe inputs sizes, a smaller number of tokens. That might be a possibility. But there are also different ways for distributed computing. It depends on what type of distributed computing you do. Some can kind of put the model onto different devices and handle handle batches like that. So for instance, if you remove the number of GPU restriction I had in my code, it would run on multiple GPUs, and I think it splits up the batch size. In this case, I think would multiply the batch size if you have 4 GPUs by 4, and then each GPU gets 16, but still you're processing 64 training examples at the same time, and then you average the gradients from the different GPUs. In that way, you can use larger batch sizes if you have multiple GPUs. That's another option. But yeah, it's fundamentally a limitation of matrix multiplication in memory. For example, if you have only access to one GPU, that could be challenging.
Great. We're still with Anna. She's asking, how can an individual, like graduate student, train a transformer for data for which there is no pre-trained transformer available? Is it even possible resource-wise?
Yeah, good question. I haven't done this myself yet. I think based on what I've seen from papers where people have done that, for example, this protein sequence paper, training from scratch looked very scary in terms of what resources they had to use in order to make that happen. And if the only case is like maybe if you have a small data set, maybe that might be feasible, but I think then maybe the transformer won't be the best option if you only have a small data set for pre-training. Then maybe using a classic RNN or even a back of words model might be a better approach. But yeah, I don't have, unfortunately, a good answer for that. I think that's a concern I have too. If you, I personally also don't have access to a large cluster where I could do that. And even if I would have access to that, I think all the engineering efforts that go into setting this up is also kind of challenging. So companies, so far as I know, have really large teams of engineers that only really focus on the coding part just to run the model on these multiple devices and GPUs. I mean, there are APIs that make that simpler, but I think in practice, it's still not very easy to do that. So you need to have like experts doing that. But maybe I'm wrong, so I don't want to discourage anyone from trying this out in practice, but I don't have a better answer at that moment.
Mm-hmm. Nice. Back to PyData, I have personally fine-tuned a pre-trained GPT-2 model, which has 117 million parameters with about 2,600 mid-sized text, around 70 lines each, and talk with me 15 minutes in, I think.
That's nice. Okay. Huh. So on a very small 3,000 data point, okay, I didn't expect it to perform that well. That is actually cool. So 107 million, it would be the size of GPT-1 approximately. That is impressive. I think that sounds very promising then. So forget what I said in the previous answer. Maybe it is possible to really pre-train them on a small data set. So yeah.
Great. A question from Sujana. Why is layer norm used and not batch norm?
That is a good question. Why is layer norm used and not batch norm? I think it has something to do with the fact that we have a sequence. So you normalize across the sequence and not across across the batches. But top of my head, I don't have a good answer. I could. I think I was thinking about that at some point, but I forgot. I think it's the way we normalize over the batches in a way. It's a good question. Another thing is batch norm doesn't really perform well if you have batch sizes smaller than 32 or 16, but I don't think this is the answer. I think the answer is more about the way we normalize this. I would have to think about this again, why layer norm and not batch norm. Good question.
Great. I think this concludes the Q&A session for this talk. Thank you so much, Dr. Sebastian. And back to you, Afnan.
Thank you, Hassan. Thank you, Dr. Sebastian. Sebastian, can you share the slides or the code that you show us on the chat so we can post it on the Twitter?
Yep. Let me do it right away. I have this GitHub repository here. And the GitHub repository has a link to the slides. I can also post it separately. Oops. It's right here.
Oh, thank you. Great. So we definitely want to give a huge thank you for you, Sebastian. This was super insightful and hopeful. And thank you, everyone, for joining. And please follow us on Twitter for more details about upcoming talks. And see you soon. Thank you.
Yeah, thank you so much, everyone, for attending, and also very good questions. Sorry for rushing a little bit about or through the topics. I don't know. It's like I always want to talk about so many things, and there's only so little time. But I appreciate your patience and joining me here today. That was fun, and I really liked your questions. That was cool. All right. Yeah. Then have a great rest of the day, everyone.
Okay.
Bye-bye.
Thank you. Bye-bye. Bye.